Sorry, I didn't introduce myself. My name is Thomas Delteil. I'm a machine learning scientist at Amazon AI. I'm involved in the MXNet team, and I'm a MXNet committer to the MXNet project. And today I'm going to tell you a bit more about how you can speed up deep learning training and inferencing. And the entire idea around that is because a lot of time the speed of training and the speed of inferencing is directly related to costs. Infrastructure costs and like maintenance costs. So also opportunity costs, because one thing that's important is the more time you spend iterating and training, the less time you can experiment. And the more you can experiment, the more you can get more complex models and you can get ahead of the competition. So the first part of how I'm going to show you how you can tackle this is knowing your model and optimizing your code with MXNet Gluon. So he's going to touch on a few things that Cyrus was saying in the previous talk, how you can use all these tools in order to maximize efficiency. And I'm going to give you some practical tips, 5 sets of practical tips, and each of them is a one-liner that can move your training speed from 1x, reference of 1x to 5x. The second one will be, we'll see how you can use SageMaker. You probably heard a lot of SageMaker today. SageMaker is inherently distributed, and it supports now with MXNet dynamic training. So we'll see what that is. And we'll see how you can get faster prediction with Elastic Inference, SageMaker Neo, and the deep learning compiler, and AWS Inferentia, which is going to be released next year. So common problem is that deep learning model training is slow. Who has trained deep learning model before? A lot of you. So I hope you can relate to that. You start training, sometimes it takes a few hours, sometimes it takes a few days, and if you're not happy with the final result, then you start again. So common solution, throw more hardware at it. So you start with a GPU, so you're already quite happy. That's a P3, let's say a P3 2x large, already start to cost like $4 an hour, so it's already an investment. And then you want to make it faster. So what you do, you move to a P3 8x large. So that's almost 4 times more expensive, but you have 4 GPUs. So you see your performance increasing, and then you add 4 more, that's 16x large. And then you're like, okay, it's still not fast enough. What do? Multi-host training. So multi-host, multi-GPU training, you start adding more and more hosts, and the bill starts getting higher and higher. And then you need to start asking your boss, can I actually really do that? Well, you see, like, we work with very large customers at AWS, and what we see them is they throw even more and more hardware. But that's the last one, I promise, otherwise, it was too much work. So you can see it starts to be very, very expensive, and you start thinking either a smarter way to approach the problem. So the smarter solution is to start by optimizing your code, making sure that you use fully this hardware that you're buying from us or renting from us. So let's sneak peek to the last part of the talk, which is that's a GPU utilization graph. And we see the more and more, as we add performance tricks, you can see the GPU utilization getting better and better, and the time to train being smaller and smaller. So there are a lot of deep learning frameworks. Why we focus on MXNet and why AWS picked MXNet is because of how well it scales and how fast you can train. Cyrus was presenting Gluon, how it's superior to Symbolic because it's easy to prototype, very, very fast. You can iterate from your ID, from a model that you've seen in a paper, to actually having something training. It's debuggable. When I have more time, usually when I do like this, more like practical workshop, I actually show how you can fire up PyCharm and actually put breakpoints and do the things that Cyrus was describing earlier. It's hybridizable. So that's the idea is you can go from a dynamic graph that you define through Python to a static symbolic graph in one line, and then this graph is going to be executed and optimized with the MXNet backend engine, and that's what you're going to train. So with one line, then you lose the debuggability because this graph is optimized. You might have some operators which are fused, but then you get the performance. But hopefully, you've done your debugging before. And also, it's fast and scalable. So even if Gluon is like super nice to work with, you can still do multi-GPU, multi-host training with it. I need just a few lines. So debuggable, I just wanted to show you, I'm not actually going to do the live demo, but that's, if you recognize PyCharm, I put like a conditional breakpoint in my training loop, and here I'm just looking at my convolutional kernels from my first layer. So you can really see that my network here has learned to detect patterns, because each of them is like a 7x7 representation of the weights of my first layer convolutional kernels. So how do you go at visualizing your training? The first thing you need to do is to make sure you visualize your network, and you make sure that you know that the architecture you define is the one you actually wanted. So with MXNet, you can use, you have built-in integration with GraphViz and also with MXBoard. And also you can get a summary where what's really important, we're talking about debugging shapes. You can see the shapes at every step of the way. And Gluon has the deferred initialization, which means you don't need to say what's your input at each layer. You just say what's the output at each layer, then you pass data through it, and based on your input shape, it's going to determine, you're going to find out what are the shapes of all your weights and of all your feature maps at every layer. So it's very, very useful. You can use the same network definition across many, many different sizes of inputs, because the weights are only going to be initialized after the first time you pass the data in. And also what I really like to do is when I create a new network, is look at the actual values of the number of parameters. Because sometimes you don't really know. It's hard to tell. You're going to put like 2 dense layers with like 4,000 units in each, and you don't realize that you just created 16 million parameters. Okay, so that's the kind of thing that you need to pay attention, because if you create maybe a too complex network for the size of your data set, your training is not going to converge well, or it's going to be prone to overfitting. So visualizing your network, making sure that you actually built what you meant to build is the first step, because that can have a massive impact on your performance. If you have like too many weights, your training is going to be super slow. The next one is to actually monitor your hardware. And I would say that's maybe the most critical one. You want to make sure that you're utilizing your GPU at 100%. So for that, I use something called GPU_monitor. You can find it on GitHub. You just Google GPU_monitor GitHub. It ties in NVIDIA drivers and InfluxDB and Grafana to give you this kind of graph out of the box. So I always kind of run that. You can use NVIDIA SMI. I guess most of you are using that. But this really gives you this time-based graphs that are really critical to understand the patterns in your utilization and see where you can do efforts in order to maximize it. And CPU is also very important. So you want to make sure that you're using your cores, for example, to do asynchronous preprocessing, or you don't want also to have them all maxed out, because then you know that you have an issue, and you need to maybe do some offline preprocessing before your training, so that your CPU doesn't become your bottleneck. What you want to avoid is starvation of your GPU. These GPUs, they're like beasts, like the NVIDIA V100 at 120,000 billion operations per second. That's as much as a fastest supercomputer from 2004. So you want to make sure it requires actually skill to build a data pipeline to feed this GPU, to not have them waiting for the data. And we'll see how with Gluon is just one line in order to do that. Yes? Yep. Yeah. So I'll go back to this and how you can erase these patterns. And for example, here, because like to do one forward pass on your network, you're not going to be able to see it at that scale. Like one forward pass might be a few tens of milliseconds. Here, this is especially going to tell you, like if it's slow, then it's going to be average. So what you want to do is this kind of seesaw patterns you see here. I mean, it's a spoiler for the next step, but it's like I/O issues, right? And then if you have bottleneck inside your network, you're going to see it at the maximum utilization average. So you have different patterns for different problems. And for example, if you want to really know where your computation is happening inside a single pass, you can use a profiler. So MXNet comes with a profiler, where you can just set start and stop. and then you get like a profiling information like you would with any other programs. And you can see, like my convolution took that many milliseconds, my dense layer that many milliseconds, that much memory has been allocated, which thread I've allocated what, and you can visualize all that in Chrome using the Chrome profiling tools. So it's really cool. But I'm not covering that in this talk, but we can chat about it afterwards. So the system performance is one thing, and then I'm going to tell you how you can really tricks to get better throughput. But you need to not forget that throughput is useless if you don't get the accuracy that you want. If you throw more thousands of images through your network, that's a nice metric to look at. But the most important thing is how long it takes to reach a certain accuracy. So for that, MXBoard is great. So MXBoard is a plugin from MXNet where you can write to the TensorBoard log format, and then you can visualize all your training directly in TensorBoard. And obviously, you have like all these images and graph and scalar and text thing you can do. So the actual performance tricks. For example, someone has an idea of the problem that you see. So that's the same training 5 times, 6 times. Who can tell me what's the issue here on the first training? Who has a guess? Exactly, yes. So the data I/O pipeline. What happens here is one batch of data goes through the network, and then the GPU is like, OK, give me the next batch. And then because all the processing is happening on the same thread, then the CPU starts, OK, I'm going to resize the next batch, prepare it, it's ready, then send it to the GPU. So that's extremely inefficient. So to solve that, what you can do is you can do asynchronous processing of your data using multiple workers in the background. That what they're going to do, they're going to prepare your batches of data, put them in shared memory, and the next time your GPU is ready to get the data is copied across straight away to the GPU. Sorry? They should. Not all do. That's the thing. Hybridization is what we talked about, which is when you actually convert this dynamic graph to symbolic and it's executed on the MXNet backend. So here you see we go from about 90% GPU utilization, which is already extremely good for deep learning frameworks, to maybe like 94. Then the next thing we can do is you can increase your batch size. Because sometimes if you use like a too small batch size, your GPU is not going to be able to use all these thousands of parallel cores in order to process the data in parallel. So to make sure that you use a big enough batch size so that you maximize the parallelization capabilities of your GPU. And see we get another small improvement, and we're almost already at 100% GPU utilization, which is extremely good. Then the next thing we can do, I won't go into details about that because usually they requires a bit of knowledge of Gluon, but remember how I said next time the GPU is ready to get the data, you just copy across the data to GPU because it's already prepared? What you can do, how about you just copy the data even before the GPU needs it? So you copy the data, it's already on the GPU, and when it's finished to do one batch, forward pass, backward pass, update of the way, the next training batch is already on the GPU. And it's 2 lines of code in order to do that in Gluon. So you have like these complex tricks that you can implement extremely easily, and something that might be extremely hard to do in TensorFlow or require some deep engineering knowledge in order to use like multi-process pools and do your own asynchronous data loading. With Gluon, we build the API so that it's very easy for you to do that. And the next improvement is mixed precision training. So instead of using float 32, use float 16. And the latest NVIDIA GPUs, the Volta V100, they have specific tensor cores to do extremely efficient mixed operations. So you get like a 2x improvement in speed. And also because you use less memory, you can increase again your batch size and train even faster. So let's go through this checklist, the different ideas I covered. You use the optimized framework. So here also it echoes a little bit to what we said this morning about AWS providing optimized TensorFlow binaries. Well, that's true, but especially for MXNet. So MXNet, we build the MXNet release that we do on PIP. They're optimized for AWS and AWS EC2 instances. For the multiprocessing, It's just one argument in your data loader in Gluon. You just say, I want that many workers. So if people are familiar with PyTorch, same principle, except we actually optimize the data loader architecture compared to PyTorch. So with the latest release of MXNet, you'll see that the data loader are not going to go to sleep between epochs. It's like you're iterating forever. And the little dips that you see sometimes between epochs are going to disappear. The hybridization that we talked about, which is like this great feature that goes from like imperative and dynamic graph to symbolic one, is just one line. You just say hybridize. To increase the batch size, just one argument of your data loader. You just say as much as you want, and then it's going to prepare these batches asynchronously on multiple workers. To avoid blocking I/O, well, I won't go into details, but one thing you need to avoid is to have synchronous calls in your training to make sure that as much as possible is done in the MXNet asynchronous threaded engine. And for mixed precision, you might think it's a complex thing to do. Well, you just cast your network to float 16, and that's it. And then suddenly you start training on float 16. So again, to reiterate what I said earlier, what is performance? It's not only throughput, it's time to accuracy. So what you can do on top of actually optimizing your code is to do hyperparameter tuning, which is a SageMaker automatic model tuning, because maybe your choice of optimizer, your choice of learning rate schedule, your choice of number of layers, that's going to impact greatly how fast your model is training. So once you get, I would say, 80% of the way where you get a good model that does about what you want and that you have maximized your GPU utilization, next step is to actually go and do this automatic model tuning. Just to give you an example, it was a few months ago, we had an intern who released the fastest training of Cypher 10 on a single GPU. And this trick was not like groundbreaking research. He just instrumented the training code of Cypher 10 with ResNet 50 to have like a bunch of hyperparameters, like the different learning rate schedule and so on. And then he managed to train Cypher 10 in 3 minutes. And the previous best training time was 14 minutes. And that's only through using SageMaker automatic model tuning that managed to find this exact combination of hyperparameters that gave the best performance. So to summarize this first part, so the recommended workflow, use Gluon to debug and iterate quickly. We've seen you can use a PyCharm debugger. You can visualize everything you want and anything you want. Visualize the performance of your hardware. Make sure that you reach this 90 plus GPU utilization, and then hybridize and optimize for speed. Finally, last step, hyperparameter tuning with SageMaker automatic model tuning. Find this best combination of parameters that are going to give you the best performance for your training. Because most of you I've heard before, you're like engineers or even data scientists, but usually your model, you don't train it once. You're going to train it many, many, many times. So you want to make sure that your training script is top-notch before you put it in this like CI/CD pipeline where you get every week a new model, right? So it's really worth taking the time to optimize your model at that point in time. So the next part, I'm going to tell you how you can scale your training with SageMaker and SageMaker dynamic training. Because once you reach this 100% utilization, then that's when you actually need to start adding more and more GPUs and more hosts to your training script. So SageMaker, just to summarize, for people who are not familiar with it, it's an end-to-end machine learning platform. Zero setup. You literally just go. You can actually create an instance from the UI, and you can train any framework you want. So you might have realized I'm a big advocate of MXNet, but if you want to use TensorFlow, I'm not going to be mad at you. You pay by the second. So when you use SageMaker, one of the things that really struck me the first time I used it was I run one of the, I think there is 100 examples, Python notebooks you can just like click and use straight away from SageMaker. What really struck me was they told me I was built for 19 seconds of training. So I run the script, and it says, OK, 19 seconds is billable. So instead of having this big instance that you use as your workhorse, it's fine if you're AWS like me, because I don't pay my AWS bill. It's just my boss pays it. Well, if you have to account for the resource you use, you don't want to be using big machines and just have them like sitting around when you go for lunch and so on. So SageMaker lets you have like a very tiny machine to drive your execution and run the actual training scripts on big clusters of P3 instances and whatnot, and you'll just build for what you use. So the distributed training of the aspect of SageMaker, you basically pick either CPU or GPU machines. You say how many instances you want. You have a training script, TensorFlow, MXNet, scikit-learn. You can also bring your own Docker container if you want, if we don't have the estimators that you require. And then it's going to start this training job on a cluster. And when the training is finished, your model is going to be saved to S3. And then the cluster is going to go down. And if you want to deploy this trained model, it's just one more command. And then you get another cluster based on ECS, which is going to serve your inference requests. So fairly powerful. With dynamic training and MXNet, we went one step further. We said, for example, one of the problems is so many people have these reserved pools of P3 instances that sometimes in big corporation, like some people, they're going to use one. They're going to do their data scientists are going to use one, another one needs two. But then you might have a bunch of P3 instances that are sitting around idle. With dynamic training, you can add instances to your training during training. So you don't say at the beginning, I need 6 instances, I need 10 instances, I need 20 or 256. During training, if you have available unpreempted P3 instances, for example, they just get added to your cluster. Because otherwise, they would be useless, sitting there idle. And if someone needs one, they get removed. So you can, between epochs, add and remove instances to your training. And it can reduce cost to train by 15 to 50% and time to train by 15 to 30%. So that's just the beginning. We literally just released that a few weeks ago, and it's only going to get better. And very soon, we're going to integrate with spot instances as well. So if it makes sense for you to below a certain cost threshold, then you can add the spot instances to your training, and then they get removed if it becomes too expensive. So that's for training. What about inference? Cyrus said earlier that most of the money, for example, for the Chick-fil-A example, most of the money is spent at inference time. When you have like 2,000 stores and you want all these like cameras to do like inferencing, that's where the big builds are going to come. So we're going to see 3 different things. We're going to see elastic inference, SageMaker Neo for compiling these models, and AWS Inferentia. So I just mentioned the deployment. So how deployment works is you can actually specify which models you want to deploy. The models you've trained in SageMaker, they manage for you. They're not just files sitting around. They actually, you can reference them in SageMaker, and you can say, I want to deploy this model, and this model, and this model. And you can split your traffic across each endpoint. And you can do your A/B testing like that. And you pick which instance you want. But most of the times, you have this problem with deep learning, which is training is fairly slow, but you add more and more machine, then it gets manageable. Then inference is fairly fast on CPU, but sometimes it's not fast enough. For example, for a neural style transfer, you do that on CPU, it's going to be 10 seconds per image. And if your app has like some nice filters that are based on this neural style transfer that you do in the cloud, well, you cannot wait 10 seconds. So it means you need to deploy on GPU. But deploying inference model on GPU, that's very expensive because you need, if you have many, many models, you need that many instances. These models, they take space in memory. Very quickly, it becomes unmanageable. So our customers told us they spend 90% of their costs on inference in production. And you see usually very low utilization of these P3 instances. We see between 10 to 30% utilization. And it's just not practical. So a lot of people, they have to sacrifice speed for cost. So it's a trade-off that becomes a lot more critical in deep learning application than other applications. Especially that when you do inference, most of the time you do inference at the batch size of 1, right? Because your customer usually sends one request at a time, and except if you do like some smart dynamic batching, most of the time you're going to run a forward pass through your network with a single element, which is not very efficient, because that's not what GPU has been made for. That's not why GPU are so used in deep learning. It's not because they're fast, it's because they can parallelize across many matrix operation. So what elastic inference does, it basically lets you pick slices of GPU. Because most of the times you want a GPU because it's fast, because you want the latency. You don't really care about the throughput. Well, at training time, sometimes you see you're training at 6,000 images per second and you're very happy. That's one thing, but maybe you don't have 6,000 customers sending you images every second. But what you want is this very low latency. So elastic inference lets you do that. Lets you just say, I want very, very fast, but I don't need that much capacity. And it's also scalable. It goes between 1 teraflop to 32 teraflops. It's integrated with Amazon EC2, even outside of SageMaker, or inside SageMaker as well. You can specify, when you create these deployment clusters, you can say, OK, I want, let's say, a C4 or C5 with a deep learning accelerator. And you support single and mixed operations. So this model that you train with Float 16, we've seen how you got like twice improvement instead of training speed. Well, you can get the same stuff at inference time. So just to give you a point of comparison, here we were looking at the cost versus speed. So here you see like basically with the P2X large, you're going to pay 90 cents per hour for your inference. But if you do a C5 plus a small accelerator, you get about the same latency and the same number of images per second for a quarter of the price. So for people who deploy a lot of models in production, a lot of deep learning models, that can be a very, very cost-effective solution. So that's for inference. That's how you can get elastic hardware to your models. But even more, you can actually optimize the speeds of your model specifically for your target. We mentioned TVM earlier, which is this open source deep learning compiler. We took that and we optimized it and we improved it and we made SageMaker Neo. So training is really done on GPU, but the models can be deployed anywhere. We're talking about edge deployment earlier. You can maybe deploy sometimes in mobile apps. You might deploy on, in the cloud or on GPU. You have like a variety of targets. And if you remember the slide from this morning, at MXNet, we pride ourselves to integrating with all this acceleration library. So for example, if you want to run TensorRT in MXNet, you can. We're going to split the graph so that it's optimized through TensorRT for part of the execution, and another part is going to be run maybe on MKLDNN because it's going to be faster. But you see this complexity, which means every framework needs to optimize for every target. And the integrations start to become a bit messier. I've seen the code, we start to be, OK, should we find a better way of doing that? So that's where TVM and Neo comes into play. So instead of integrating every architecture into your framework, what you do is you have one common layer where you can represent Neo. Basically what it does, it takes your model and converts it to tensor operation. And then each platform has the best way of doing this tensor multiplication. So you're going to use CUDA on GPUs. You're going to use like a different type of vectorized operation depending on how many cache you have on your CPU. And that's going to be different from an Intel platform, from an ARM platform. And then you have all these accelerator chips that have their own way of doing these vectorized matrix operations. So it's a lot saner way to do, where you just need, each platforms need to integrate with Neo, and each framework needs to integrate with Neo. And then it's just like a one-to-one instead of a many-to-many. So under the hood, what does it work? You have many, in deep learning, probably a lot of you are familiar with deep learning, how it is. What it is really is just a computational graph, right? Like you have some input, lots of operation, you get an output. So that's this graph that you can optimize. First, TensorFlow, MXNet, Onyx, they all get converted into this unified graph representation. And that's when you start to be able to say, okay, I'm going to combine these two operations together. I'm going to reuse this memory buffer because I don't need it in the next iteration step, and so on. So that's graph level optimization. You don't need to know actually much about what these operations are. And then the next step is a tensor operation. So depending on the size of your tensors and depending on where they are in the graph, you can optimize the memory layout. So it's extremely sensitive. When you do this kind of optimization, it's really, I don't know if all of you picked up on what Cyrus was saying on the channel first and channel last. And we say you put to channel first, and then MXNet is twice faster than TensorFlow. That's a lot to do with how the GPU reads the memory. When you do channel last, basically in the RAM, your memory is laid out as all your R pixel, then all your G pixel, and all your B pixel, because the memory is 2D. It's like a bitmap. But if you have images that are RGB, it's 3 dimensions. So you need some way to flatten it. Depending on how you flatten it, your cache access is going to be different, and that's where you can get massive performance improvements. So Neo look at that and optimize the tensors for speed. And then for each target, architecture specific, you convert this tensor operation to machine code that is really made for fast execution. So architecture specific optimization can be up to 12 times faster than the stock frameworks, and up to 100 times smaller memory footprint. When you think about it, MXNet, TensorFlow, their libraries with like so many operators. You can do all sorts of convolution, transpose convolution, pooling, average pooling, batch norm, layer norm, and whatnot. You have so many, and every week someone comes up with a new operator that gets implemented into the libraries. But your model that you just trained, you might just use like 5 or 6 different operators in it. You don't need to bring the entire MXNet or the entire TensorFlow with you on your deployment platform. So what it does, it only compare, because they only compare to machine code, you just need a runtime that's able to run this tensor operation, and it can be in total like 100 times smaller. For example, the runtime for Neo is about 1 megabyte. And some version of TensorFlow are more than 100 megabytes, depending on what library you statically link with it. So, and I come to the last part, which has been announced at reInvent. This is called AWS Inferencia. Inferencia is a custom chip that's going to be built by Amazon. It's up to 10 times faster deep learning inference, so hundreds of teraflops, or thousands even of teraflops. And it's going to be available this year, so stay tuned. So instead of, it's going to be available through the Elastic Inference, and you'll be able to attach to any of your EC2 instance this custom AI accelerator and run your inference a lot faster. So any questions? Yes? So between Neo is it's a service in SageMaker where you basically say, sorry? So Neo takes your graph, whether it's in a TensorFlow trained model or a MXNet trained model, takes the graph, takes the weights, and is going to compile this graph into optimized machine code. That's basically, instead of having a library like TensorFlow or MXNet that says, okay, when you see this node, you do this piece of code, when you see this node, you do this piece of code, among all the possible operations, it compiles all this stuff to machine code for the specific architecture, right? So you get CUDA code if you target NVIDIA, you get machine instruction for ARM. If you target ARM, you get, for CPU, you get different set of instructions. It's really, what you get is like a .so file, basically, that can get executed on specific architecture. Inferencia is hardware. So it's not on the software anymore. It's like an actual physical chip that you will be able to say, okay, link that to my EC2 instance, and then use this specific optimized hardware for deep learning and run this, because the chip is going to have like, instead of like general purpose transistors like any CPU, the chip is made for the specific kind of operation that you do in deep learning, convolutions, pooling, and matrix multiplication, and all this stuff. Yeah, it's going to be a specific hardware in-house built. If one of our competitors has something similar, if you know what I think about. Yeah. Yes? Neo? Yep. Yep. Yeah, so if you go through the documentation of Neo, you get a list of compatible architecture. So if I showed you the code, it's really, in SageMaker, you have like your model, you do model.compile, and you say which architecture you want. And then you get a compiled model artifact in S3. And then this, you can run it. It's going to be run through a specific Docker container. And you can use that to do inference on your, either directly in SageMaker by, let's say you targeted C5, and then you run it on a C5 inside the cloud, or you can run it, you can target Raspberry Pi, and you can run that on the Raspberry Pi, for example. Yes? I'm not exactly sure for mobile, but what you can do if you want to target mobile, you can use the open source version, TVM, and target ARM as your compilation platform. And then you can use TVM to run that on your mobile app. So Neo can take the TF-Lite format. Oh, you mean SageMaker in general? Can it save in TF-Lite? Yeah, so if you use TensorFlow, basically SageMaker works if you provide your own training code and your own saving code. So if you provide TensorFlow training code and your saving code, you say like export as TF-Lite or whatever, that's what is going to be saved in S3. So that's going to be your artifact. And then you get that and you deploy it the way you want. You can deploy it with SageMaker, or you can take it and deploy it in-house or on a mobile app or whatever. So you can use SageMaker as much or as little as you want, whether just for training or for inference or compilation. You can use it like end-to-end. You can come in at any time of the deep learning kind of pipeline. Yes? It's going to be, I think, only inside AWS. I don't know, is the answer. So when we're going to get closer to the release, there's going to be more information available. Yes? So SageMaker ARL is implemented on top of TensorFlow and MXNet. So MXNet supports reinforcement learning, and we have example implementation in the repo, like DQN, and I think we have PPO as well. We don't have a toolkit per se, same way as we have Glue on CV or Glue on NLP, but we have a lot of reference implementation, and you can use SageMaker ARL that integrates with Coach in order to use SageMaker and MXNet together to do reinforcement learning. Yes. And actually, SageMaker ARL is based on, with MXNet, is based on Gluon. So if you want, you can do online learning with MXNet the same way as you can do it with TensorFlow. Is simply you need to architect your own, you need to architect your application so that you can keep adding examples to your training set and then refine your model. So I think it's more like a architecture question. MXNet supports it like any other framework. is what I say. And Gluon makes it easy because when you train one batch, you're not like fitting one batch. Right? You just say, pass the data through, compute the gradient, update. So you can pass like small batch, big batch. It's extremely flexible. It's dynamic. Yes? Yes, so we just released a beta version of a book that is called Dive into Deep Learning. If you come at the end, I'll give you the actual URL, or maybe if we have time, I'll just put it up. It's more than 100 different Jupyter notebooks that goes through the theory of deep learning. So if you're kind of, you come from the ML background, but you want to know more about deep learning, it's going to go through the different optimizers, Adam, Adagrad, SGD, SGD with momentum, so on and so forth. And every practical implementation or every practical example is done with MXNet and Gluon. So it's kind of a learning. You learn the practical side and you learn the theoretical side at the same time. And you start with like these basic building blocks, and at the end you do stuff like object detection, image segmentation, text machine, neural machine translation, very advanced NLP and CV techniques, or recommender system is another chapter. So really kind of try to, and that's a course that's being taught next January at Berkeley. So we have Alex Mola, we probably know from the SVM papers, is a principal scientist or even like director of science at AWS, and he's going to teach this course at Berkeley from January. So you can access the same material, and you can follow at your own pace. It's called Dive into Deep Learning. I'll put it up at the end of the talk if you want. Any other questions? OK. So I think we're almost at the end of the talk, actually. So to summarize the kind of 3 steps I was talking about, first is optimize your training code to fully utilize your hardware. Extremely important and very much underestimated. There was this one time, I can't name the customer, but we're working with a customer that was evaluating between different cloud providers and different like type of deep learning hardware. And we went, they were like, well, you know, we're not too sure if MX is actually faster. We looked at the code, and using the same hardware, we managed to get 64 times speed improvement, just optimizing the code. So just to tell you how critical it is, and even like top class data scientists might not have the engineering background to do the right data pipelining. And with Gluon, we're really aware of that, and we put in all this nice asynchronous processing and multi-processing right into the framework and make it very easily accessible. Train at the lowest code possible using SageMaker. So SageMaker has this really nice paradigm where you decouple the experiment management from the actual training. So you don't need a massive machine to run a Jupyter notebook. You need a big one to run your training scripts. And that's what SageMaker does for you. It starts a cluster from 1 to n instances, do your training, and when it's over, it goes down, and you only bill for what you use. You can use dynamic training with MXNet. So even during a single training job, you can add and remove instances dynamically to make sure none of your P3 instances are sitting idle. And finally, for inference, what we do, we can optimize the model. We can optimize the deep learning models, compile them to be super tiny, super efficient, and optimize for specific deployment targets, specific architecture. And you can deploy that with SageMaker on an auto-scaling cluster using Docker containers, and it's all handled for you. And finally, you can also use, next year, custom hardware to really have like the lowest cost and the fastest inference possible with AWS Inference. So thank you very much. If there is any questions, we still have a bit of time, so I'm going to take a few if there's still. Yes? Yes, so I've recently been made a committer, so if you create a pull request, I can merge it. So that's also something maybe we haven't really touched on, which is MXNet it's Apache MXNet. So it's part of the Apache Software Foundation, which means inside the MXNet team, people who are actively contributing to it, we have people from Intel, NVIDIA, Airbnb, whatnot. We have plenty of companies who have bet on MXNet. You've seen the slide with all the customers we have. And they're all actively contributing to MXNet one way or another. So we have people from Mathematica who are actively using MXNet and contributing new operators to support their own research. And any of you could join the project. And if you have like sustained contribution, any of you could be made a committer of MXNet. It's not owned by AWS. We bet on it because we think it's the fastest, most scalable framework out there. And we want you to use it because then you're going to save money, and then you're going to stay customers of us. But we don't have skin in the game. We're not selling MXNet to you. You want to use TensorFlow, use TensorFlow. We just think that if you use the MXNet, you're going to spend less money and you're going to get better models, right?
Contribution is not just contributing to the engine. It's also contributing examples, contributing notebooks, contributing implementation of your application, research what you do. This can all be included, right? So it doesn't mean that you have to be writing the operator.
Me? Yes. Yeah, overall in the usability, MXNet with Gluon is like a winner by large margin. In terms of performance, don't trust me, but look at NVIDIA, who is like kind of this neutral player in the field. They just want people to use GPUs. They don't care if it's MXNet or TensorFlow. They just published a benchmark where they show that for ResNet 50 training, MXNet is 50% faster. Okay? And then one thing I'll give to TensorFlow right now is they have a larger community because they were there the first, and Google has done some incredible research. So lots of papers coming from Google, they've already been implemented in TensorFlow. And as you all know, usually you want to just play around with something. You're going to take it from whatever paper, whatever framework it is, and you're going to run with that. So to tackle this problem, we created the toolkits, computer vision and NLP, and we have other verticals coming. For example, if you've heard of the BERT paper, which is like latest NLP paper that shows that you can actually do very efficient transfer learning with NLP, was published a month ago. We already have the implementation with state-of-the-art result and pre-trained model in Gluon NLP. So we're following closely the bleeding edge research, providing reference implementation for it and integrating it in our toolkits. So it becomes like a one-stop shop for you to go there, look at the training code. So the actual like pre-trained model we give, they are actually trained in our CI/CD pipeline, stored on S3, and we give you the actual training commands you need in order to get the exact same result, and the training script, and the model definition. So there's nothing hidden. It's really, what we do is really in the open, because we believe that in openness and reproducibility in research, and that's what's going to make us progress even faster, which in a field that is already like super fast. With respect to MXNet itself, or? So MXNet, we're exploring a bunch of options. For example, we have like this. Recently, we integrated the fact that the graph, you mean like the engine part? I mean, there's so many things, like especially in Amazon research. So lots of teams in Amazon are using, for example, you've heard of like Textract to do OCR and extract documents. All the teams inside Amazon, they're migrating to MXNet. And I know because my team, we are providing advice, the type of optimization. I just tell you, we help this team to implement them. So there's a bunch of like new research happening on MXNet, but well, lots of papers, they don't publish, it's framework agnostic, right? So I think it's a good thing that the researchers are not saying that's PyTorch research or that's TensorFlow research, right? Like what's important is the network, the implementation. We don't really care that much, and that's why you don't see that many papers referencing the framework they used, because it's not framework specific what they're doing. I would pick PyTorch. Yeah. No, really, the usability is everything. Anybody who's actually done...
Usability plus maybe support of the Onyx, say,
yeah.
slot something to the world.
Yeah.
It is fun.
Yeah, I think with they just released last week PyTorch 1.0. I think they added these capabilities in the latest release. So I'm gonna, excuse me, AV. I'm just gonna put put a website, which is this dive. Oh, okay. Oh no. Dive into. Wow. Okay, so it's dive into deeplearning.org. Ah, no. I might have some Word document. I hope it's nothing critical. Oops. And this cannot be zoomed. Well, can you dive into deep learning has more chapters now? Yeah, yeah. And it's also on GitHub. You can, yeah, if you Google dive into deep learning. Yeah, if you Google dive into deep learning, or if you go on the website, there is a link directly to GitHub, to the repo, and you have all the notebooks, and you can contribute pull requests to it if you find any mistakes. And yeah, feel free to continue helping spreading deep learning to the world. Okay, thank you.